Welcome to the Area Solutions channel. In this video, I am going to be demonstrating the way and manner one can determine the position vector of a force for a three-dimensional system. And we're going to use this system that is shown to work out position vectors for different conditions of forces, and as it is useful to estimate moment about different points. Well, the importance of estimating position vectors is to be able to calculate the moment about specific points, and in order to do that, it's also important that one is able to take a force in three-dimensional space to its component form. So we are going to walk through a series of problems beginning from this one, and we're going to use this as a first case study to illustrate how the moment of this force, this 5,000 Newton force, can be determined about any point. And to do that, we're going to first take the first two components, then we determine the position vector about one particular point or the other. So to begin with, we are going to try to estimate the moment of this 5,000 Newton force. Let's say we are going to look for the moment of this 5,000 Newton force about point 0. And to find the moment of that 5,000 Newton force about point 0, we need to look for two items, and one of them is to take the force, which is 5,000 newtons, to its component form, and that will mean this will be equal to Fxi plus Fyj plus Fzk. So our first responsibility then will be to determine the different terms, the different components, which are Fx, Fy, and Fz. To find Fx, Fy, and Fz, one needs to take into consideration what has been given in the question. For this case, the 5,000 Newton force is at an angle of 40 degrees to the z-axis, and is also at an angle of 50 degrees to the s-axis. Obviously, because this force is resting on the xz plane, one can say that the same force is at an angle of 90 degrees to the y-axis. So having these different direction angles for the force, we can quickly find each and all of the components of the force. Beginning from Fs, Fs will be equal to F, the value of F times cosine of the angle it's making with the x-axis. So the value is 5,000, so we have Fs is equal to 5,000 times cosine of the angle. For this case, it's making angle of 50 degrees with the x-axis. So we have this times cos 50 degrees, which will be equal to 3213.51. And likewise, we are looking for Fy as well. Fy will be equal to the magnitude of the force, which is 5,000, multiplied by the angle, cosine of the angle that it's making with the y-axis. For this case, is 90 degrees, and that will give us 0. And finally, Fz, which is the last part of the force, will be the product of the magnitude of the force, which is 5,000, multiplied by cosine of the angle it's making with the z-axis. For this case, the angle is making with the z-axis is 40 degrees. And if we evaluate that, we are going to get 3829.93 meters. So one can write out the force in its component form simply to be F is equal to 3213.51 I. Then for the y-axis, we had 0j. And finally, for the z-axis, there's something else that is very important as well, the sense of the force. If we resolve this 500 Newton force to the z-axis, is going to be pointing in this direction as shown, and this direction is opposite the direction of the z-axis. So for the value of the z component, we're going to get a negative of it, which is minus 3829.93 K. So invariably we've gotten our force taken to component form. And after this is done, the next thing, because we are to look for the moment about O, we are going to find the position vector of the force which is acting at point C about O. And to find this position vector, we need certain displacement value Rs, I, Ry, J, and Rz, K. To find this position vector or the components of the position vector, we may need to quickly identify what these values are. The first one is Rx. To get Rs, we are looking at how one can travel from this point C to point O. And to travel from point C to point O, one may need to travel along this x-axis first. To travel along this x-axis, one would have moved a distance of 80 meters. But we must understand that for this case, because we are looking for position vector, we are going to evaluate the displacement from point O to point C. And to evaluate the movement from point O to point C, one would observe that it's going to begin by first traveling along the x-axis, that 8 meters, that 80 meters that we've estimated earlier. So one may need to travel first, or alternatively, to make it easier to move from point O to point C, we're going to commence by first looking at the displacement along the y-axis. So there's going to be a movement along the y-axis up to the top part of the box. And to move along the y-axis to the top part of the box, one would have traveled a dimension Ry is equal to 200 meters. And it is positive. It is positive because moving from point O to the top of the box, one would have traveled positively along the y-axis by a dimension of 200 meters. Then to go to point C, one may then need to travel parallel to the x-axis by another dimension which is equal to 80 meters. And one would observe that in moving from this point which is on top of the box to the extreme of the box, trying to locate the S position, one would have moved 80 meters that we had earlier. And it's going to be positive because the movement from A to C in the direction of the x-axis is in line with the positive direction of x. So we have Rx to be 80 meters as well. And finally, Rz. To get to C, having traveled upwards in the y direction and moved horizontally in the s direction, one may then need to travel along the z-axis to get to point C. And that dimension is equivalent to 70 meters. And one would observe that if one is traveling down to point C, one will be moving in a direction that is opposite the z-axis. And because it's opposite the z-axis, we get our Rz to be equal to negative, that's minus 70 meters. So invariably, one would say that our RCO is equal to 80I plus 200J minus 70K. And this is our position vector. So just to recap, we quickly was able to get our value of F in its component form to be 323.51 plus 0J minus 3829.93K. And having gotten that, we're able to find our RCO, which is the position vector of the force, 5,000 Newton force from the point O. And we got that that is equal to 80I plus 200J minus 70K. And we said that to get that, we're just moving from O to point C. And to move from O to point C, we have to move along the y-axis upwards to top of the box by a dimension 200 meters, which is in line with the direction of the y-axis. Then by the time we got to top of the box, we have to also travel down the x-axis by a particular distance, which we understood that, of course, if we get to top of the bus and we travel along the x-axis, we understood that that is equal to 80 meters, which is the length of the bus in the x-axis. And because we are traveling rightwards, we took it to be plus 80 in the x-axis. And finally, to get to C position, we have to move by dimension in the z-axis. And we're moving against the direction of the z-axis because we are moving inwards into the bus, and that dimensions, we said it is 70 meters. And because it's 70 meters and is against the z-axis, we add it as negative 70. Now once this is done, it is easy to estimate the moment from here. We know that moment is equal to r cross f, and for this case, to get r cross f means we have to put in all values I, j, k, and we put in our position vector r, which we've obtained here, to be 80 and 200 and minus 70. And finally we introduce our force component, which is 3213.51. we had 0 for the j component, and finally we had minus 3829.93. And if you evaluate this by calculating the determinant of that matrix, work out that simply, you're going to get a moment value for minus 766319i and minus 5314459.145j and minus 642782k. And to get the value of the moment in terms of magnitude is going to be 1132629 newtons meters. Now this is just to demonstrate that you must be able to evaluate the position vector and the force taken to component to be able to estimate moments. But notwithstanding, we are going to walk through other scenarios to be able to grasp fully how the position vector is estimated and also how the force is taken to components and eventually estimate moments. So we're going to quickly walk through a second case scenario wherein we will look for the moment about point D. Let's not forget that we've estimated our force before, our force component to be equal to 3213.51 I plus 0g minus 3831.24 k. But for this case, we are looking for moment about point D. So we are going to be estimating the position vector that is needed to calculate the moment of the force acting at point C about position D. So we are going to move from point D to point C swiftly to determine RSI, RYJ, and RZK. So to move from point D to point C, one would have to travel. First and foremost, let's observe that the distance from O, from the origin to point D, is 120 meters, while the distance from the origin to point C is 80 meters. So if one is to travel from point D to point C, obviously it means that one will move backwards from this 120 meter to the point where we add 80 meters. And we know that the difference between 80 meters and 120 meters is 40 meters. So obviously, to get to the point where this force is acting, one will have to travel backward first by 40 meters, which is along the x-axis. So we have RS to be equal to minus 40 meters. And it's minus because we are traveling in the opposite direction of the x-axis. Then once one has moved backwards, because we are coming to see, one may need to go upwards. And to go upward to the top of the box, one would have traveled a distance of 200 meters. And because it's upwards, which is the same direction with the y-axis, we have Ry to be equal to 200 meters. And in this case, it's going to be positive. And finally, once one eventually gets to top of the bus, which likely is going to be the middle along this line, one still needs to travel along the z-axis to get the dimension in the z-axis, and that's likely it is 70 meters. And obviously, if one is to move 70 meters to the point where C is located, one will be traveling in a direction that is opposite the direction of the z-axis. So for this case, we add RZ to be minus 70 meters. And after that is done, we can write out our position vector out clearly. RD is equal to minus 40 I plus 200 J minus 70 K. Moment M is equal to R cross F, and it's just to replace all these in matrix form. We have our I, J, K values of matrix, and if you have your I, J, K values of matrix, we have that moment is equal to minus 40, that's our R values of position vectors, 200 and minus 70. Then our first values, we had 3213, 3213, we had 0 for the y-axis, and we had minus 3831. If you evaluate the moment and you find the determinants, you're likely going to get 100.2695 Newton meters. Next, we are going to look at another kind of force representation in which we are not given angle that the force is making respective components, but we are given the positions of the force. So for this kind of case, that's where we have our 8,000 Newton force. To take this to components, we're going to work this out through another procedure that requires us to first look for what we call the displacement vector. Then we'll go forward to look for what we call the unit vectors. And we use the unit vectors to multiply the magnitude. Once we've done that, we can get the force, the 8,000 Newton force in its component form. So to take the 8,000 Newton force to component form, that's 8,000 Newton force to Fsi, Fyj, and Fzk, we may first need to look for the displacement Bf. For this case is Bf. That's what is the displacement of this force? What's the displacement vector of this force from point B to point F? So we're going to look for Bf, displacement vector of Bf, which is going to be, let's say, Bxi plus Byj plus Bzk. So our first struggle will be to look for Bs, By, and Bz. From what we have, Bs is the distance from B to F in the x-axis, and usually to determine that you have to look for Bs2 minus, then you subtract the value of Bs1 from it. Our Bs2 is the value of x at the end of the force. For this case, that's at position F. What is the value of, what is the x component? For this case, it is 300 newtons. So we have 300 newtons minus the Bs1. Bs1 is the value of x at B. What would be the value of x at B? The value of x at B would be the position of B in respect of the coordinate system. For this particular coordinate system, to get to B, one would have traveled from the origin, that is O, along this line to get to B. we know that the base of the bus, that's the end of the bus, is where we have our origin. So one would have moved from that base to the point of B, and the dimension will be 80 meters. And it's going to be positive. Positive because moving from 0 to this point, one will be traveling in the positive x direction. So we have this to be 300 minus 80, and this will be equal to 120 meters. Then again, for BY, we're going to have BY2 minus BY1, where BY2 is the dimension, is the value of the position of the force in the y-axis at point F, where the force is acting. For this case, BY2 is minus 100. And BY2 is minus 100, so we have to subtract the other part of it, which is BY1. BY1 is the value or the position of B in respect of, or taking reference from the origin. If you're taking reference from the origin, which is O, to B, one would have traveled upwards from O to top of the bus. And from the base, which is where O is, to top of the bus, the dimension is 200 meters. So we have 100 minus 200 meters as well. And this will be equal to minus 100 minus 200. This will be equal to minus 300 meters. And finally, BZ. BZ will be equal to the distance between the 2 points BZ2 and BZ1. So it's going to be BZ2 minus BZ1. So our concern becomes, what is BZ2 and what is BZ1? From the problem, our BZ2, which is the value in the Z, the value of Z in the F position, that's the end of the force, the 8,000 Newton force. And for this case, it's 180 meters. So we have 180 minus BZ1. BZ1 is the position of B of the bus from the origin. From the origin, which is point O, you want to get to the extreme of the bus. We know that the origin is at the center point in the z-axis. So to get to the position where B is, and B is at the extreme along the z-axis. So one will move from the origin downwards by a distance of 70 meters. And if one would travel by a distance of 70 meters from the center, we say that B would have moved by 70 meters. And it is positive because from O to B, one would have moved 70 meters, and the movement would be in the positive direction of the z-axis. So for this case, we had 70 meters. So, and this is going to be 180 minus 70 meters. So our RZ is going to be 110 meters. So a slight mistake when we're looking for BS. We had that this is 300 minus 80, and it's not 120, but it's supposed to be 220. So our displacement vector BF becomes 220I minus 300J plus 110K. And once this is done, the next thing to do is to find the magnitude of BF of our displacement vector. And the reason for this is because we may also need to estimate the unit vector. And to find the magnitude of our displacement vector, as usual, we have 220 square plus 300 square plus 110 square. And we'll find the square root of all that. And if you evaluate that, you're likely going to get 387.94 meters. So once this is done, one can easily find the unit vector of BF. The unit vector of BF will be vector BF divided by the magnitude of BF. So our unit vector BF is equal to, our vector BF is equal to 1 over 387.94 multiplied by 220I minus 300J plus 110K. So that can easily give us a value for unit vector. Once the unit vector is obtained, the next thing is to find the force components. To find force components, our force, that's 8,000 newtons force that we have, to take it to component is equal to the magnitude of the force, which is 8,000, multiplied by the unit vector of the force. So if we do that, we get 8,000 newtons multiplied by the whole of the unit vector, which is 1 over 387.94. All of this multiplying 220I minus 300J plus 110K. And if this is evaluated carefully, our value of force, F of 8,000, would be equal to 4536.75 I minus 6186.47 J plus 2268.37 K. And this is our force in its component form. Let's not forget the way we got our force in component form. Another simpler way is to quickly get the position of this force at point B. The position of this force at point B would be, if you're moving from the origin, which is O, to point B, what will be the values? The values would be in the x-axis. One would have traveled from O to this point, which is 80. Then one would have traveled in the y-axis from down to up, which is 200. And finally, one would have traveled from O, this O to A, to point A, which is going to be minus 70. So using the difference between 2 points, one can easily find the displacement vector and the unit vector. Once the unit vector is obtained, one can multiply the value by the 8,000 Newton force to get the force in its components. But before we wrap up, one may want to determine the moment of this force, say about any point. And let's quickly illustrate this by looking for the moment of this force. Let's say about A. Let's say we want to look for the moment of this force B about point A. If you want to look for the moment of force B about point A, you may need to find the position vector of that force from point B to point A. And if you want to evaluate the position vector from point A to point, you want to evaluate the position vector, you have to move from point A to point B. And to move from point A to point B, one may travel in the x-axis, in the direction of the x-axis. But first and foremost, let's write out that this is equal to Rs plus Ry plus Rz. This is I, this is J, and this is K. So we need values for Rs, we need value for Ry, we need value for Rz. Rs, Rz, and Ry. First, to move from point A to point B, one may first travel along the z-axis direction by a distance of 70 meters, and it's going to be positive because it is in the same direction with the z-axis. So we have our Rz to be 70. Then by the time one gets to this end, the person may need to travel again along the b-axis by a distance that is equivalent to the distance of, or the dimension of, this box, which is 80 meters as shown on the top. So this is 80 meters, and if one is moving downwards, it's going to move in the positive direction of x-axis. So we have our Rx to be 80 meters. And finally, Ry. For we to get to B from A, we discovered that we didn't move downwards or upwards. It's still on this plane. So because we are not moving downwards or upwards, so we have that our Ry value will be 0. So our position vector RBA will be equal to 80I plus 0G plus 70K. And once this is obtained, one can easily find the moment of the 8,000 Newton force about, say, A. and that will be equal to R cross F. And if it's R cross F, the next thing is to write out all our values I, J, and K. We bring in the values for the R, which is 80, 0, and 70. Then after that is done, the next thing is to bring in your value of force. Our force component, which is 4536I, and we had minus 6186J, and finally 2268K. And if you evaluate the moment, one will get a value for moment M. Of course, 8,000 about A will be equal to 433053I plus 499042J minus 494918K. And if you find the magnitude of this value of moment, you will get 8255.43.1 Newton meters. And that's the moment of the force of the 8,000 Newton force about point A. So we've looked at this system. We've looked at how a force acting on the XZ plane can be taken to component form, and we saw how you can estimate the moment after calculating the position, after determining the position vector about a particular position. Then we went further to look at this force system that is 10,000 newtons acting on the XY plane, such that it's perpendicular to the Z axis, having an angle of 90 degrees to the Z axis. We took this force to component form by multiplying by cosine of the angle it's making with each of the axes. Then we also determine position vector of this force about any point and how that could be used to estimate moments. Then finally, we looked at another kind of force system wherein we had to look for how this force can be taken to component form, then how we can determine the position vector of about any position for this particular force. So obviously, we've looked at this system as a whole. So if one, for example, is asked to determine the sum of forces and the sum of moments about any point, or the question can come in a form wherein we are asked to replace the whole of this force system, the whole of the forces acting on this system, by a singular force and a moment at a point, maybe A, maybe at point G, maybe at point O, maybe at point C, whatever the point is. If you are asked to replace the whole of this system by just one singular force and one couple, is to find the resultant of these forces, that is, you take all of them to their components, you add up these respective forces in component form, and that's the one singular form that will be used to replace all the forces acting on the system. Then you find the sum of the moments in their component form, and the sum of moments obviously will be equivalent to one singular moment at that point. So by the time you replace the whole of this system by just that one force and that one moment, you would have resolved your problem. Alternatively, the question could require you to find an unknown force. Maybe for this case, you have to find one of the forces, and they'll give you the values of moment, or they give you the values of resultant force, and they give you specific values. You walk through the problem following the same procedure. By the end of the day, the difference is that you end up getting a simultaneous equation. Once you get your simultaneous equation, you can find the unknown from your simultaneous equation. And I think that will be all for now. I really do appreciate your time, and I do hope that the video was illustrative enough. And bye for now.